Hi folks, so I am going to go through some notes that will help you with lesson 1 of the summer assignment. If you look at the summer assignment, it is divided into lessons. Lesson 1 is the first 2 pages. So these notes will help you with that. If you already know how to do everything on those 2 pages, you do not have to watch this video. I also gave you a handout where you can take notes on the video. Again, if you already know how to do the assignment, you do not have to do this. The only thing that's required is the assignment itself. This other stuff you will not be handing in. But if you think you would find it helpful, you can take your notes on here. You'll notice that for the examples and the problems, I put the problem itself on the left-hand side with some space for you to write the solution. So write what I'm writing on the slides. And then on the right-hand side, I left space for you to put notes. So what I'm envisioning there would be anything that you think would be helpful for you to use when you do these similar problems on the summer assignment, meaning anything I say or anything you think of from your previous chemistry class. So I'm going to start out by talking about atomic mass and molar mass and how they are related. So atomic mass, and this is the definition that you probably got in your intro chem class, weighted average of all the naturally occurring isotopes. Weighted average just means we take the atomic mass of the isotope and we multiply it by the percentage. So that's what this little formula is showing you. Okay, so what this formula says is that, let's say there are 4 isotopes of some particular atom. To find the atomic mass, you'll take the mass of the first isotope. That's what I mean by isotope 1. And then you multiply that by the percentage of that isotope. That's percentage 1. I also put that you should put the percentage in decimal form. And then you do the same thing for all of the isotopes and add them all together. So if you've never seen a formula like this, it's a pretty common way of writing formulas where you see like dot, 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 and then it ends with N, massive isotope N. Okay, all that means is if N would be however many isotopes you have. So if you have 4, you would go up to isotope 4. If you have 2, then you go up to isotope 2. So this formula is just, the N just means that we can use it for any problem that we see. So the first type of problem is when you're given all of that information and you use that formula to figure out the atomic mass. So here, you would take the first isotope, magnesium-24, and the atomic masses are in the parentheses. So I'm going to take 23.98504 and multiply it by the percentage. But remember, the formula says percentage in the decimal form, so don't write 78.70. Instead, you're going to move the decimal point back 2 spaces. So the decimal form, in case you forgot, of a percentage is just the decimal point moved to the left 2 spaces. And then I'll do the same thing for the second one. And then for the third one. So then when you do that out, you just do it out on your calculator and you get 24.3095. The unit for that is something called AMU, which stands for atomic mass unit. You also might just see U sometimes because you already know it's the atomic mass. That's what the problem said. So you might see U, but usually you'll see AMU, atomic mass unit. So the unit for atomic mass, AMU. The other way that this type of question might be asked is if you're given the atomic mass and you kind of have to work backwards. Okay, so in this question, you're given the final answer and you're given two isotopes. So we have lithium 6, which has the mass of 6.0151, lithium 7, which has the mass of 7.0160. So what you're looking for here is the percentages, okay? So what we do know is that we have two naturally occurring isotopes. We also know that they're going to be some combination that adds up to 100%. Okay, that's the only two we have. So if you look back at this one, magnesium had 3 isotopes. If you add up all those percentages, it comes out to 100. So here, lithium has 2. We know they need to be 100. Also remember that in our formula, we're going to be using the decimal forms of the percentages, okay? So instead of 100, it will be 1. Because if you have 100% and you move the decimal point back 2 spaces, you get 1. So our decimal form of 100% is going to be 1. So all that is to say, this is what we would figure out here. One of our isotopes is going to be X%, and one is going to be 1 minus X. So now we can use the formula with our decimal percentages being X and 1 minus X. So all I'm going to do is take the mass of the lithium isotope and multiply it by the percentage. In this case, that's going to be X. Then you're going to take the mass of lithium 7 and multiply that by its percentage, which in this case is 1 minus X. And you know that is equal to what's given in the problem as the atomic mass. So then you solve this. I'm not going to go through solving it. It's just a regular algebra problem. I know you can all do that. So when you solve this, you get that X equals 0.075. So what that means is that lithium 6, whoops, is 7.5%, because remember lithium 6 we set as X. So our X came out to this, and then we turn it into a percentage for our final answer. So 7.5%. And then lithium 7 was 1 minus X. So 1 minus X is this. So when we change that into a percent, we get 92.5% lithium 7. So the next section of this lesson of the summer assignment is the mole. Now the mole you're probably familiar with from your intro class. The mole is a counting unit, just like a dozen. So like a dozen would have 12, a mole has 6.02 times 10 to the 23rd. You can use that for anything that you want to count. We also tend to use something called the molar mass a lot more frequently in chemistry than we actually use the atomic mass. And that's because the molar mass has a unit of grams, and we can actually measure grams in the lab. So we use the molar mass a lot. What's nice is that the atomic mass is the same as the molar mass, except we just change the unit. So once you find the atomic mass of something, it automatically is the molar mass. So 1 mole of magnesium, which we found up here, very beginning, 24.3, 1 mole of magnesium has 24.3 grams. So we found the atomic mass of magnesium to be 24.3 AMU. And if we're looking for the molar mass, it's 24.3 grams. So that is the mass of 1 mole of magnesium. So 6.022 times 10 to the 23rd atoms of magnesium. So for compounds, the formula for molar mass is going to be this. And you see that we have another dot, dot, dot in our formula. Okay, so the molar mass of one of the elements times the subscript of that element. And then the molar mass of another element times the subscript of that element. And then you keep going until you're done with all the elements. So the N here just means if you have 2 elements in the formula, you just need to do it twice. If you have 3, do it 3 times, and so on. So to find the molar mass, what you're going to do is look up the decimal number for each element on the periodic table. Now, a lot of them can be rounded. So like carbon is 12.01, but you can just say 12. And it says in your summer assignment, most common ones that are rounded. So for carbon, we're going to have 12. And then we multiply it by the subscript for carbon. And you know that if there's no subscript there, it's a 1. Then we do hydrogen, which the molar mass on the periodic table is 1. And we have 3 of them because we have a subscript of 3. And then we do Cl, which is 35.4, somewhere around there, depending on the periodic table you're looking at. And we have 1 of them. Then you just plug this into your calculator. And you get 50.4 grams. Next one we're going to do, you'll see it has parentheses because there's a polyatomic ion in this one. So the parentheses are going to get distributed. The 2 gets distributed in the parentheses. Now, because magnesium is outside the parentheses, it's not affected by the 2. The 2 is distributed to the P and the O. So all you do is multiply the subscript. So for P, we would multiply the subscript of 1 times 2. And then for O, we'll do 4 times 2. So for magnesium, our decimal number on our periodic table is 24.3. We're going to multiply by our subscript of 3. We'll add that to phosphorus. The decimal number of phosphorus is 31. We're going to multiply that by 2. So you'll see the subscript is a 1 at first, but then because of the 2, because phosphorus is in the parentheses, we have a 2. And then for oxygen, it's 16, and we have a total of 8 here. So when you do that math out, you get this. The last example here is something called a hydrate. Now, if you're a senior going into your senior year, you probably did a lab with a hydrate in your intro chem class where you had like blue crystals and then you heated them up with a Bunsen burner and they became white because you dehydrated them. That's a hydrate. If you are going into your junior year, You obviously didn't have the opportunity to do that, but we're just gonna, it's not really a big deal. We might even do it this year. So here we have a hydrate. So what it means is you have the chemical formula and then you have some amount of water also in the formula. So in that lab, we evaporated the water out with the Bunsen burner and then we could figure out how much water was in it. So in order to figure out how many of each atom you have, you're going to take the coefficient and multiply it by the subscript of anything after it. So here you would have 14 hydrogens, 7 times 2, and 7 more oxygens, okay, because you already have 4 before it. So that coefficient, it's kind of like in balancing. Where we distribute the coefficient, you do the same thing here. So for magnesium, we have 24.3, and we only have 1. Sulfur is 32, and we have 1. Now here you have a choice. You can lump all the oxygens together or not. It really doesn't matter. I'm going to do them separately just so that the notes are easy to follow. So that's going to be my first batch of oxygen. Hydrogen, our molar mass is 1 and we have 14 of them. And then we have our second batch of oxygen and we have a total of 7 of those. So when you do out that math, you get 246.3. So the last 2 problems I'm going to do are mole conversions. So this is also known as composition stoichiometry. And all that means is that it's stoichiometry, but there's just one substance in the problem. So we have composition stoichiometry and reaction stoichiometry. Reaction will have you're going from one substance to another. Here you'll see there's just one substance in the problem, ammonium chloride. So for those of you who had me for chemistry, I'm going to teach it the same way right now with the unicorn chart and everything. For those of you who did not, please do this however you feel comfortable doing them. But if you would like to use the unicorn chart, I did put it on Classroom attached to this assignment. So you will see that there's something called a quick guide for stoichiometry. So in there, there's steps that I'm going to follow to solve these problems. There's this unicorn diagram. And then there are something called conversion factors. Okay, so that's what I'll be using. Again, if you already know how to do stoichiometry and you feel comfortable with it, don't learn a new way. Absolutely not. But if you would like to have a refresher, this is what I'll be using, and you do have access to it. So here we're looking for formula units, and we are given grams. Now, formula units are just another form of particle. We say usually you'll see formula units for an ionic compound, which ammonium chloride is, and you'll see molecules for covalent compound. People are usually more familiar with the term molecules. We tend to use it more. But formula units, just if you see that, it's the same thing. It's just for an ionic compound. So the first step on our stoichiometry quick guide, start with what you're given. So that would be the number in the units. Write both parts of your units, put your given over 1. Now, a lot of people don't include the 1. It's absolutely not necessary to put your given over 1. The reason I do is because it helps people see, helps students see the dimensional analysis that the units are canceling out, which is the whole point of this. But if you do not include the 1, you're not going to get points off on the AP test at all. So I'm going to take my given, which is 4.52 grams of ammonium chloride. And I'm going to put it over 1, and that's going to be a factor. Now you'll notice that it says both parts of your units, and it says it in big all caps letters. For the most part, people ignore that in intro chem. You need to stop ignoring that now. You will, on your FRQs, you're going to need to have both parts of your units to get full credit on some of them. So here, what that means is the metric unit, like grams, liters, moles, and the substance. So the formula that, or the symbol that goes with it. So here, this is what I mean by one part of the unit, and this is the other part of the unit. Okay, so you really need to make sure you are doing that from now on. So that's step number 1. Step number 2, use the unicorn diagram to determine the number of factors. So here's the unicorn diagram. We just need this side of it for composition stoichiometry. So if once we get to reaction stoich, we'll use the other side as well. So for right now, just use this side and you can ignore the A. I'll explain what that is when we get to the reaction stoich stuff. So for right now, ignore the A. Particles are atoms, formula units, or molecules for the most part. Particles can be protons, electrons, whatever, but this is what you're usually going to see. Atoms, formula units, and molecules. So in this question, we are going from grams to particles, okay? Because the question gave us grams, that's our given, and we need to end at particles. So to figure out the number of factors, you take the shortest path possible. But you'll notice that on this diagram, grams and particles are not connected. Okay, they don't have a road going from grams to particles. So you have to go from grams to moles to particles. Okay, so it's kind of like connecting flights. Like I hate connecting flights because I don't like flying. So I prefer a direct flight from grams to particles. But when I went to Montana, there was no direct flight from Boston to Montana because no one really wants to go to Montana. So I had to stop in Denver and then go to Montana, okay? So if you're at grams, you have to go to moles before you can go to particles. Each unit gets a factor. So grams is going to be 1 factor, moles will get another factor, and particles will get a 3rd factor. So I'm going to write out 3 factors. So that takes care of step number 2. Step number 3 says drop down both parts of your units. This should start to seem very familiar, and you definitely did this in your chemistry classes. You take both parts of your units from 1 factor, so grams NH4Cl, and put it on the bottom of the next factor. So now, number 4, the unicorn diagram not only tells you the number of factors, it also tells you what units go on top of the factors. Because remember we said each unit gets a factor. The unit that's here goes on top of the factor, okay? So if our first one had grams on top, which it did because it was the given, the next place we went was moles. So this is what goes on top of our second factor. And this diagram is meant to apply to all problems. So you're never going to see the second part of the unit there, and that's okay. You just need to remember because it's very important. So we're going to put moles of NH4Cl on the top. And then step number 5 says, keep repeating this steps 3 and 4, until all of your factors have units. So step 3, drop down. Step 4, figure out what goes on the top. So we're going to put moles of NH4Cl on the bottom. And then the unit that goes on top, you can either look to the diagram and figure out where you went next, which we went to particles, or you can just write what you're looking for, because what you're looking for should always go on the top of the last factor. So now all of our factors have units, and we need to figure out the numbers. So the way that works is that you match up the units with those conversion factors, which were on the second part of the quick guide that I posted. So here in this second factor, we have moles on the top and grams on the bottom. And again, you're not going to see the second part of the unit because we want this to apply for all problems. So we go here, we find the factor that has moles on the top and grams on the bottom. So you just copy these numbers. So 1 goes with moles, and then X is the molar mass. That's what we were just finding before. So 1, we're going to write for moles. And then X, you find the molar mass of NH4Cl. Which is 53.4. So then for the next factor, you find the one that has formula units, which you know is a particle, and on top and moles on the bottom. Particles on top, moles on the bottom is this one right here. So I'm just going to plug in Avogadro's number on top and 1 on the bottom. My original one says 6.02. I believe the formula sheet for the AP test has the second 2. It really doesn't matter. And then you do that math out, and you get this. All right, the last problem has a lot more in it, but it's the same basic idea. So the last problem, you're given 114 milligrams of sucrose, and you're looking for atoms of hydrogen. Now, at first glance, this might look like a reaction stoichiometry problem because it has 2 different substances. But if you read the question carefully, first of all, there's no reaction. But second, it's saying how many atoms of hydrogen are a part of 114 milligrams of sucrose. So the first thing you might notice is that we have milligrams here. On all of our stoichiometry stuff, we talk about grams. Molar mass is in grams. We need to make this number in grams. Okay, so we're going to convert milligrams to grams. To do that, you put milligrams on the bottom so that they cancel out. And we're going to put grams on the top. Now, there's a bunch of different ways to write this conversion factor. There are 1,000 milligrams in 1 gram. So that's one way to write it. 1 gram has 1,000 milligrams. You can also write 10 to the negative third grams is in 1 milligram. However you want to write it, it's fine. The answer that you're going to get is this. So the next thing I'm going to do is take grams of sucrose and convert it into particles of sucrose, okay? Because we're eventually trying to get to particles of hydrogen. Now, I'm going to do this in 3 different steps. I did the conversion to grams. Now I'm going to do the conversion to particles of sucrose, and then the conversion to particles of hydrogen. You can do this all in one line as well, okay? So if that makes more sense to you and you want to do this all in one big, long conversion, that's fine too. I think it's easier to understand this way. So for this one, you're going to start with your new grams as you're given. And then we're going to do the same thing that we did for the question right before this one. So I'm not really going to spend too much time on that because we just did it. So we're going to drop down the units. The unit that goes on top is the next one on the little chart. And we're going to need 3 factors for this because we're going from grams to particles. You can write particles if you want, but since this is a covalent compound, it's also a molecule. So then you plug in your numbers. 1 goes with moles here. The molar mass of sucrose is 342. Then we have 1 and Avogadro's number here. So when you do that out, you get this. But believe it or not, we're still not done because that's not what the question asked for. It did not ask for molecules of C12H22O11. It asked for atoms of hydrogen. Okay, so we have to take that number and do one more conversion. We're going to put molecules of sucrose on the bottom because we want to cancel that out. And we're going to put atoms of hydrogen on the top. Now for the number here, you're not going to find this on the conversion factors because it's not really the stoichiometry part. You're going to look at the formula. Okay, so you know, based on this formula right here, for every 1 sucrose, there are 22 hydrogens. That's what the subscript tells you. Every time you have 1 molecule of sucrose, you have 22 hydrogens in there. So for 1 molecule, you have 22 atoms of hydrogen. So that's how you're going to figure out the final answer. So 4.42 times 10 to the 21st atoms of hydrogen. If you have any questions after watching this video, that is totally fine. Give the problems a shot. You'll notice at the bottom of the second page has the answers to the exercises for this lesson. So check your work, check your answers as you go along. And then if you still have questions, I will have a Google Meet on Monday, July 5th at 3 p.m. to go over lesson one of the summer assignment. So you can come there with questions. We absolutely can go over any of the notes, any of the problems that you're having trouble with.